Okay, so now moving on to non-ideal behavior. So whenever you are dealing with a non-ideal gas, you need to account for that by using this compressibility factor. So it's just this Z term. You have to start accounting for that, but in order to calculate Z, you need the reduced pressure and reduced temperature. So reduced pressure, PR, is going to be equal to the actual pressure over that component's critical pressure. And the critical pressure is just the pressure, like the highest pressure at which that system, that component will exist as like a two-phase system. And then similar for the reduced temperature, it's going to be T over TC. And you can get these PC and TC values from B1, appendix B1, and PC and TC are component specific. So it'll depend on like what you're working with. So like N2 or H2, and you can figure out, you'll be able to figure out from B1 what that PC value and TC value is for that component, and then figure out the reduced properties. And if you end up having a mixture, you'll have to use K's rule in order to get here, because since these are component specific PC and TC, if you end up having a mixture, you need to do a weighted average of those pure component values. So like for TC, it would be the mole fraction of component A times component A's critical temperature, and then you add the mole fraction of component B times component B's critical temperature. And then you would just calculate the reduced temperature, same as you did before, except you would now be using this weighted TC value. And then same for critical pressure, so it would be the mole fraction of A times A's critical pressure plus the mole fraction of B times B's critical pressure. And then the reduced pressure would just be the pressure over the weighted critical pressure.